Good afternoon. We are Group 8, consisting of Evin Joy, Sabina George, and Jagadeesh Kumar Sellappan. And our capstone as was, can a small openly licensed language model become a competent medical question answering assistant without a data center budget? So the short answer is yes. So as you can see, 60.8% accuracy on held out medical board style questions, training under 1% of a 7 billion parameter model on a single GPU in under an hour. I will cover the problem and data. Sabina takes methods and model design. Jagadish presents results and next steps. So with that, let me continue with the problem. Clinicians and trainees already use conversational AI for quick clinical questions, but the model that perform best on medical exams, the MedPalm, GPT-4, are proprietary and also costly per query. For a hospital that can't send protected patient contests to an external API also brings out a safety concern. Open weight model solves the privacy and cost problem, but out of the bots, they are weaker. So our research question is, how much medical competence can a small team recover from a 7 to 8 billion parameter open model using cheap adaptation techniques? One important framing point is that we position this as an educational and reference aid for students and clinicians, explicitly not a diagnostic authority. And that shapes how we evaluate it and how we would deploy it. So our data comes from 3 public research licensed medical QA. Basically the benchmarks which we actually cleaned and unified into a single schema, just under 200,000 questions total. So MedMCQA is the bulk, about 187,000 questions across 21 medical subjects with short factual stems. The MedQA adds roughly 11,000 USMLE board questions, which are long clinical vignettes. But PubMedQA contributes 1,000 yes or no or maybe questions, which are answered against a research abstract, which is testing grounded reasoning rather than recall. So note the log scale. In MedMCQA, which is dominating by volume, and the other two serve as smaller, high-quality benchmarks. So 3 findings from exploratory analysis actually changed how we build the model. First, cleaning. The sources were curated, no missing questions or answers, but we normalized Unicode and HTML and removed 43 invalid items and 56 duplicates. Second, the prompt length. Even at the 95th percentile, a full prompt stays under 500 tokens. So we can train on complete untruncated examples. Third and most important, we found a shortcut hiding in the data in MedMCQA. Option A is correct, 29% of the time, while D is only 21%. A model could learn to guess A instead of learning medicine. So during training, we randomly shuffle the option order and remap the gold label that neutralizes the bias while preserving the clinical content. With that, I hand over to Sabina for how we build the models.
Thanks, Evin. One last check before modeling: how the derived numeric features relate to each other. Most strong correlations here are uninteresting. Word and character length are the same variable, and the options versus context relationship is structural. The important row is the last one. The position of the correct answer is uncorrelated with every length feature, so answer or question length doesn't leak the right choice. Combined with option shuffling, the corpus has no obvious shortcut a model could exploit instead of learning medicine. On the right, prompt length confirms every dataset fits comfortably inside the model's context window. We built two models deliberately. On the left, a baseline implemented completely from scratch, a transformer answer selection network in PyTorch. We wrote the multi-head self-attention and encoder blocks ourselves rather than calling PyTorch's built-in transformer. So every architectural choice is ours. It's 3.6 million parameters fully trained. Its purpose isn't to win, it's an honest reference for what you get with no external medical knowledge. On the right is a real system, Mistral 7B, an open weight model adapted with QLoRA. The pre-trained weights are compressed to 4-bit and completely frozen. We inject small trainable low rank matrices adapters into the attention and feed forward layers and train only those. That's 42 million trainable parameters, just over half a percent of the model. This is what makes a 7 billion parameter fine tune possible on one GPU. Here's how the baseline works. Worth a moment because we built every piece. Each question is paired with each of its four options, forming four sequences: a classification token, a question, a separator, then one option. Those get token plus learned position embeddings and pass through two prenorm encoder blocks: forehead scale dot product self attention and a GLU field forward network with residual connections and layer normalization. We pool at the classification position and score it with a linear layer, giving one number per option. A softmax over the four scores produces the answer distribution trained with cross entropy loss. The whole network is 3.6 million parameters, small enough to train fully on a laptop, which is what we wanted from a transparent baseline. This table is the practical side of training both models. The baseline trains on 30,000 items with cross entropy over the four options. Adam W 4 epochs, about 2 minutes on a M3 Max laptop. The QLoRA fine-tuned formats 8,000 examples as instructions and trains with casual language modeling laws using the paged 8-bit Adam W optimizer to keep memory in check. One epoch about 47 minutes on a single A100. Two things to note: both models train on the same cleaned corpus with options order shuffled, so neither can exploit answer position. And the held out evaluation questions are completely disjoint from training. So, what you will see next is genuine generalization, not memorization. Over to Jagdeesh for the results.
Thank you, Sabina. Here are the headline numbers. Measured on 500 held out questions the models never saw. Random guessing on 4 option questions gives you 25%. Our from scratch transformer reached 29.1%, barely above chance. The QLoRA fine tuned Mistral 7B reached 60.8%. That's 31.7 percentage point improvement over the from scratch model. And we got it by training just 0.58% of the model's parameter on one GPU in under an hour. For context, that accuracy is in the same range as published open medical models like Meditron and PMC Llama, which is a strong showing given our very modest training budget. But the most interesting part of this chart is the third bar, and that's what I want to unpack next. This slide is our most interesting finding, and it came from an experiment we almost didn't run. We evaluated the base Mistral model, zero shot, no fine tuning at all, on the same 500 questions It scored 55.4%. So decompose the journey going from our from scratch model to the pre-trained base model buys you 26.3 points. That's pre-training, all the medical text the model absorbed before we ever touched it. Then QLoRA fine-tuning takes it from 55.4% to 60.8%, a further 5.4 increase, which is about a 12% relative reduction in error. To be honest, fine-tuning helped and the gain is real and repeatable, but it's not where most of the competence comes from. The pre-trained backbone does the heavy lifting. That's more useful than fine-tuning works because it tells you to invest in better base models and grounding, not just more epochs. A quick word on how the models actually learned because the diagnosis matters. On the left is the baseline training curve. The loss falls slowly from 1.40 to about 1.36 and then validation accuracy climbs steadily but plateaus just above chance around 29%. Crucially, training and validation move together. There is no divergence between them. That pattern is underfitting, not overfitting, a high bias model. A compact network with no external medical knowledge simply can't represent the reasoning these questions demand. More layers wouldn't fix it. The fine-tuned model behaved very differently. Its loss dropped to 0.93 within a single epoch, and because the validation questions are disjoint from training and we only trained one epoch, the 60.8% reflects real generalization rather than memorization. We also tuned the model rather than accepting the first configuration that worked. The most important knob in QLoRA is the adapter rank. Essentially, how much capacity you give the trainable part. We ran a control sweep, identical data, identical epochs, varying only the rank. Rank 8 gave 59.2% and rank 16 gave 60%, the best, and rank 32 actually dropped to 57.6%. That shape is textbook. Too little capacity underfits, too much starts to overfit the training data. Rank 16 is the sweet spot, and this validates the configurations we used for the full run that produced 60.8%. Remaining optimization we would do next: tuning the learning rate and epoch count, scaling up the training set toward the full 200,000 questions, and comparing base models.
We want to be clear about the limits of what we build. First and most important, this is an educational and reference site. It must not direct patient care actually, and any deployment needs that disclaimer attached to every question. Second of all, benchmark performance is not clinical performance, and at some questions are clean and self-contained, and the real clinical questions are messy and open-ended. Third, be honest about the number. At 60.8%, the model is wrong on roughly 2 out of 5 questions, and the language models tend to be fluent and confident even when wrong. Surfacing calibrated uncertainty is essential before anyone relies on it. And finally, we know of specific data issues, OCR style character noise in the MedMCQA test, and class imbalance in the PubMed question answers, which skew towards yes.
4 directions if we continued. On modeling, finish hyperparameter search, train on more of the 200,000 question corpus, and compare larger base models. Given that pre-training does the heavy lifting, a stronger base is the highest leverage change. On grounding, add a retrieval augmentation so the model answers from the approved clinical source it can cite, instead of relying purely on what's stored in its weights that directly attacks the confident but wrong failure mode. On evaluation, move beyond multiple choice accuracy to free text metrics and expert clinical review. To productionize, serve the merged adapter, begin an inference API with guardrails, clear disclaimers, and calibrated uncertainty, validated real prospective questions rather than exam benchmarks. To summarize, we showed that a compact, openly licensed model can be adopted into a credible medical question answering system. 60.8% on held out board style questions, training under 1% of its parameters on a single GPU in under an hour. Just as importantly, by measuring the base model, we learned that most of the competence comes from pre-training and fine-tuning refines it. That's a useful finding for anyone deciding where to spend their effort. All of our code, the clean data pipeline, and the trained adapter are in the GitHub repository on screen. Thank you. We are happy to take questions.